Hello, everybody. My name is Agathiya Tharun, and I'm a freshman studying engineering here at Purdue University.
Hello, I'm Herrick Mesina, also a freshman in engineering at Purdue.
And along with Professor David Cappelleri, we wanted to develop a modular end-effector system and an autonomous mapping software as part of the Resilient Extraterrestrial Habitats project, also known as RETHi. This modular end-effector and tool changer system is designed to be compatible with various space robots that can autonomously repair and maintain resilient extraterrestrial habitats when in cooperation with an environmental mapping software. We approached this by utilizing a pneumatic system for the gripper tool end effector. Since it was implausible to carry around a pressurized air tank, a vacuum pump was employed instead. As you can see in this image, the pneumatic system for this tool changer is held in place by a PC6-01 connector mount, which also allows airflow to pass through it and to the hose on the other end. However, due to the porous nature of the material in which this prototype was 3D printed, air leakage and thus air pressure loss became an issue. Therefore, it was decided to manufacture the part from a less porous material such as aluminum.
The mapping system uses the Robot Operating System, ROS, a framework used to string together logic and inputs for robots. We simulated the robot and the world it was exploring using Gazebo, a software commonly used for said simulations. Concept prototype systems were created for the more maneuverable but less capable Turtlebot 3 in order to determine feasibility, but were then ported onto the final fetch robot, which has all the desired capabilities and platforms that we need. Several open source packages such as RTabMap, a mapping algorithm, and a 3D to 2D rangefinder projector were trialed through ROS.
The result of our methodology was successful in the sense that the connector mount has been partially manufactured and is scheduled to be completely manufactured and assembled in the near future. As seen in these images, the excess aluminum at the bottom of the part is still needed to be removed. The two center holes need to be drilled, and the tapered hole threads that fit the PC6-01 connector need to be hand tapped. Manufacturing was done at the Bechtel Innovation Design Center using the VF2 CNC mill, the horizontal bandsaw, and hand tapping tools.
Using the robot's built-in laser rangefinder and a mounted RGBD camera, we were able to let the robot loose on a simulated world and have it automatically create a 3D map of the area, as you can see from the photo. The map, as shown, was built using RTabMap's visual simultaneous localization and mapping algorithm. The fetch robot, being much larger than the Turtlebot, often had trouble navigating the tighter spaces such as thin door frames. Some changes, especially to the parameters that decided the robot's size or footprint, were vital to the system. These were all obstacles to the seamless mapping of the environment, and there is much more depth to cover in the robot's evaluation of its environment. As you might be able to see, there are plenty of optimizations to be made for both the mapping system and end effectors. For the use cases of these systems, reliability and quality would be of the utmost importance. Nonetheless, this iteration of the project brought us closer to our end goal of a robot that can navigate through a dynamically changing environment, produce end effectors that can complete maintenance, and actuate its determined tasks upon the habitat. Thank you for listening, and we hope you gained an insight as to how our work could aid the furthering of human space exploration.